In the last lecture, we saw why applied vectors should not be considered as vectors. The reason being that there are a lot of problems in defining the vector space in which applied vectors are elements of. In this lecture, we claim that applied vectors should not be indeed considered to be vectors, and there is absolutely no need in any application for them to be considered as vectors. In lecture 12.1, we have seen why the classical approach in teaching applied vectors is completely unsatisfactory. A solution to this problem appears clear once we notice that there is absolutely no need of giving the set of applied vectors any algebraic structure. For all known applications, the algebraic structure on vectors and the relationship between applied vectors and vectors below will suffice. Therefore, applied vectors will be considered purely as geometrical objects, with no algebraic operation defined on them, as opposed to vectors, which indeed are elements of a vector space by definition. There is a relationship between applied vectors and vectors. The one we will consider is the map that sends applied vectors that we have seen that by definition are pairs of vectors in a vector space V. So the applied vectors are inside the set Cartesian product of V by itself, and it will associate the vector V in a vector space V. What's the definition of this correspondence? The pair AB is being sent to B minus A. Notice that B is a vector, A is a vector. The opposite of A is well defined because it is part of the algebraic structure of V, and the sum between B and the opposite of A is still well-defined element of V, again because of the algebraic structure of a vector space. The associated vector will be routinely used to employ linear algebra theorems on geometric problems involving applied vectors. So applied vectors are very useful to give a mathematical model to some geometrical questions. However, it is much better, actually it is mandatory, not to consider them as algebraic objects. Instead, we will pass from applied vectors to vectors by means of this correspondence and apply the linear algebra theorems that we've studied in this course to these vectors associated to applied vectors in order to solve questions, geometrical questions, that have been modeled by applied vectors. Now let's consider this example to highlight what exactly I mean by the passage from applied vectors to vectors. Compute the area of the region in R squared bounded by the triangle with vertices A, B, and C. This is a purely geometrical question. Solving it using just geometrical constructions would require quite a long procedure. Here we rather use linear algebra. We cannot use it directly on this data. As we said before, linear algebra cannot be used on applied vectors. Let's see how applied vectors here play a role. We can consider the applied vectors AB and AC. We have a formula that expresses immediately the area of a triangle in function of vectors, and it involves the vector product of vectors. However, here we just have applied vectors. AB and AC are just applied vectors, and the vector product does not operate on applied vectors. Therefore, we cannot use the formula we would like to employ directly on applied vectors. Instead, let's associate to applied vectors real vectors. So intermediate step, introduce applied vectors a, b, and ac. Their associated vectors are b minus a and c minus a by the definition we have just given. And approximately b minus a is a vector which we'll denote as a point in here, because we have to subtract from b a. This is what we will get. And c minus a will roughly be here. What do we do with these two real vectors? Well, we can imagine now that we associate the applied vector, we associate the real vector even to a, seen as applied vector in itself. So that means that a should be sent to a minus a, which is the origin. Okay, so if we look at a as a applied vector on itself, then a is the pair a comma a, and the associated vector to a is going to be the origin. So this triangle can be reconstructed by real vectors as a triangular formed by the origin b minus a and c minus a. But this time all 3 points here are real vectors, they are not applied vectors anymore. This is the triangle we are considering now, and on which we can use the formula relating the area to the vector product of b minus a and c minus a, as we have seen in a previous lecture that we will remind right now. Now we can use the vector product formula on these points. In lecture 10.5 we have stated that the area of a region bounded by a triangle 0, which is the origin, b minus a and c minus a, can be expressed as the norm of the vector product of b minus a and c minus a divided by 2. Notice that this triangular region is just the translated by minus a of the given triangular region, so the area is just the same. To sum the procedure up, we started from a purely geometrical problem, the one of computing the area of this triangular region. The vertices are denoted by a, b, and c. We give a mathematical model to this geometrical problem, introducing 2 applied vectors. One is ab and the other is ac. We cannot use linear algebra on applied vectors. Therefore, we consider the real vectors associated to these applied vectors. We obtain b minus a and c minus a. The triangle now we are considering is no longer a, b, and c, but it will be the origin 0, b minus a and c minus a. On this mathematical model, we can use a formula involving vector product of vectors b minus a and c minus a, and derive the area of this triangle simply by linear algebra techniques. We notice that the area of this triangle is exactly the same as the area of the initial triangle, since this triangle is just the translated of this by the vector negative a. So we started with the geometrical situation, we gave a mathematical model introducing applied vectors. We want to use linear algebra on these objects, therefore we associate to applied vectors real vectors. We solve the problem using linear algebra on real vectors, and then we pull back the argument on the initial geometrical situation. This is a typical standard technique which involves the use of linear algebra on geometrical situations. The interface are applied vectors, but applied vectors are not algebraic objects, so we cannot use any algebra on them. Instead, we associate to applied vectors real vectors, use linear algebra, and then pull back the conclusion in the initial geometrical setting.